Great. Work through some examples together dealing with distance and displacement. We also know that displacement is the change in position of an object. And the equation, well, the unit we use for this, first off, is also the meter, the SI unit of length. Let's break down the equation for displacement just so we all know how to read these types of equations. So we have delta x equals x subscript f minus x subscript I. So this delta x, this delta symbol, means change in. It's not saying multiply, it's saying the change from one spot to another for this variable. So the change in x, which is our position. X equals position. XF is our final position, so where the object finally ends up. And XI is our initial position of our object. All right, so let's work through some examples together. So number one, is the distance of a round trip, so going somewhere then coming right back where we started, positive, negative, or 0. I recommend that for all physics problems, you first draw a picture, draw a diagram. So I'm going to try to draw it the most simple way I possibly can. So let's say I start out here. Let's just say I'm going to the grocery store and back. So here's my store. Here's me. I'm going to set my initial position as 0, as the origin, right? That's my that's my coordinate system that I'm setting up. So I start out at the 0 position. Let's say the store is 50 meters away. So if I go there and back, what is the distance I have traveled? So remember, the definition of distance is the length traveled, right? So I went 50 meters one way, 50 meters back, equals 100 meters total. Don't forget your units. So this is the total distance I have traveled, right? Like, I know that at the end of the day, I walked that far, like to the store and back, and it was 100 meters as me walking. But in physics, when we talk about systems, when we talk about items and objects that we're describing, we like to think of the displacement. So is the displacement of a round trip positive, negative, or 0? Again, displacement is your change in position. Delta x, change in position, equals final minus initial. You can think about this problem a little more conceptually, like drawing out this picture. You can also think about it in terms of the equation. Let's look at the equation first. So we are solving for delta x, that's our displacement. Our final position, well, we came home, so our final position is 0, minus, well, we started at home, so that's 0. So our total displacement is 0 meters. Again, don't forget your units. conceptually change in position. So yes, we did technically walk to the store and back, so the distance traveled is a positive number. But when we're thinking of displacement, so the change in position from start to finish or finish to start, we ended up in the same place. So that means our total displacement is 0. Let's move on to another problem involving distance and displacement. Does your car odometer measure distance, sorry y'all, distance or displacement, and why? I want you to take a second and think about this and think about the why part. Let's say you're driving and you see your car odometer in front of you on the dashboard, and you see it going up, up, up as you drive, putting miles on your car. Is it measuring distance or displacement? Does that odometer take into account direction? Does it go positive numbers one way, negative numbers another? Or does it just count total miles traveled? So your odometer measures distance, because that odometer doesn't care what direction you're going. It doesn't care if you went there and back round trip, whatever. It's going to count the total number of miles that you traveled. So that is the total distance. Next, we're going to cover some examples dealing with speed and velocity. Firstly, let us define what average speed is. So average speed is the total distance over the total time. Notice here how average speed uses distance, not displacement, distance. For our units, because units are always super duper important, so distance is in meters, time is in seconds. So our unit for average speed is meters per second. Okay, example for average speed. A bird catches fish by plunging into the water from a high height. If a bird dives from a height of 7 meters with an average speed of 4.0 meters per second, how long does it take to reach the water? Here is what I recommend you do for every single physics word problem. First, write what you know. Second, write down what you're finding. And lastly, draw a picture. Y'all, drawing pictures is super helpful for this class. It helps you conceptualize what's going on, and it can help you get a better understanding of what you're solving for. All right, what I do know. So I know that it dives from a height of 7 meters with an average speed of 4 meters per second. So I'm going to write down my knowns. So average speed equals 4.0 meters per second. And I also know, headphones, I also know that this height is actually the distance the bird travels. So I know that distance equals 7.0 meters. I'm going to draw a little picture. Oh goodness, I can't draw birds. I'm going to draw a little rectangle for birds. So this is my bird. And it travels 7 meters, that's a point here, to the water where the little fishies are, so it can eat the fishies. What I'm trying to find is the total time. When in doubt, look at what you know and look at the relevant equations. We know that average speed is distance over time. I know 2 of these variables and I can solve for the missing one. So average speed equals distance over time. I know that the average speed, I can swap in here. And then the distance, I can swap in here. So average speed, 4.0 meters per second equals 7.0 meters over time. All right. When I move time over, I get time equals 7.0 meters divided by 4.0 meters per second. Notice how here my meters cancel out and I'm left with seconds. When I plug this into my calculator, 7 divided by 4, I get a time of 1.75 seconds that it took for the bird to dive down to the surface of the water. Next question involving average speed. The red kangaroo can hop at a speed of 65 kilometers per hour. That's terrifying. How far in kilometers can it hop in 3.2 minutes at this speed? Part B says, how much time does it take to hop 0.25 kilometers at this speed? And I think we all know the answer here to both of these questions. It's just you run very far away from this kangaroo because that's a fast kangaroo. That's really scary. Okay, let's look at A. So in A, again, I recommend you write down everything you know and then write down what you're looking for. So the red kangaroo can hop at a speed of 65 kilometers per hour. All right, so that is the average speed this kangaroo can hop. So average speed equals 65 kilometers per hour. Part A, how far in kilometers can it hop in 3.2 minutes? So we know that the time we're working with is 3.2 minutes. How far, distance, can it travel? That's what we're looking for. Think back to our equation for average speed. Average speed equals distance over time. And look at this. We have 2 knowns and 1 unknown. So we know that our average speed can be swapped in, our time can be swapped in, and then we can solve for distance. But I hope you noticed that our units don't quite match up. We have kilometers per hour, then we have minutes. What's the distance? So this problem might seem straightforward, plug and chug, but you have to be careful with the units. You're going to have to convert something around so that your units are all consistent. In this case, I could convert minutes to hours or the hours to minutes so that we're all consistent in our time, unit of time. I'm actually going to convert the 3.2 minutes into hours. All right, so we're going to do some dimensional analysis here. So 3.2 minutes times, I want the minutes to cancel out, so I want minutes on the bottom and hours on the top. So there are 60 minutes per 1 hour, and this gives me, come on calculator, 3.2 divided by 60, roughly 0.05333 hours. Notice how I'm not rounding yet here. You don't want to start over rounding. I recommend you only round at the end. So now we have our time in hours, and now we can swap this into our equation. So our average speed is 65 kilometers per hour. We are looking for the distance, and we know that our time is 0.05333 hours. I am going to move this over out of the denominator. So I have 65 kilometers per hour times 0.05333, repeating, hours. The hours cancel out, so I only am left with kilometers. And when I plug this in, so 65 times 0.0533 is approximately 3.47 kilometers. Wow. That's terrifying, y'all. Like, if you ever have a kangaroo coming at you, like, just, I don't have good advice. Just run. Okay, let's look at part B for this terrifyingly fast kangaroo. So again, write down everything you know. We know that the average speed is 65 kilometers per hour. How much time does it take to hop 0.25 kilometers? So we know that the distance is 0.25 kilometers. And we're asked to find the time. So again, we're going to look at our relevant equations, and we see that the average speed equation is very relevant here. And then we look at our units to see if we need to do any converting, and nope, we're good. We're going to end up with an answer in hours. So swap this information in. 65 kilometers per hour is equal to 0.25 kilometers over, I'm going to use T for time. We are going to flippy floppy the denominator over and bring the 65 over. So we get T is equal to 0.25 kilometers over 65 kilometers per hour. You see here that the kilometers cancel and we're left with hours. So 0.25 divided by 65 is, the time we get is 0.00384 hours. I don't know about y'all, but this is hard for me to conceptualize how much of an hour that really is. So let's convert this into seconds. So some more dimensional analysis. Oop, headphone came out. So there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. This way my hours cancel, my minutes cancel, and when I multiply this through, so times 60 times 60, I get that the kangaroo runs 1/4 of a kilometer in approximately 13.8 seconds. Y'all just, if you see a red kangaroo, just run. Just run the other way. Great. So we see that we can use that average speed equation, and it relates average speed, distance, and time. So if we know 2, we can solve for the missing one. Now let's work on some examples involving average velocity. So before we were looking at average speed. Average velocity is displacement over total time. So again, notice here how we are working with displacement, not distance. So speed deals with distance. But velocity deals with displacement. And that is an important distinction because displacement involves directionality. Distance doesn't. If you hiked 100 miles, that's 100 miles distance. It doesn't tell us east, west, whatever direction, just total path traveled. Displacement, though, includes direction. Therefore, velocity also includes a direction. That is an important distinction. All right, let's go back to this equation. Let's develop it a little bit more, okay? So we have average velocity. I'm going to say AVG equals displacement over time. But remember, we know that displacement can be defined as delta x. Remember, that is the final position minus the initial position. So our average velocity equation, we can write it as delta x over delta t. Again, this means change in position. And this, the delta t, means change in time. So the total time that has happened for this motion. The unit is also in meters per second because we have displacement over time. Let's look at an example involving average velocity. You sprint 50 meters in 6 seconds, stop, and then walk slowly back to the starting line in 40 seconds. What is the average sprint velocity, the average walking velocity, and the average velocity round trip. First, I'm going to draw a picture because in this type of problem, drawing a picture really helps you conceptualize what's going on. So you are here and you sprint 50 meters. Sprint 50 meters. I'm going to say that this is my zero position, the starting position. You'll notice that for a lot of these problems, you're going to end up setting your object, like where your object starts, as the zero position, because it's a lot easier to work with, right? So you sprint, and then you get here, and, ooh, that's not a straight line. Pretend that's a straight line. And then you walk back. So here's the 50-meter mark. Here's the 0-meter mark. So you're asked to calculate the average velocity for when you sprint, for when you walk, and then putting the two together. What does velocity tell us, though? There are two things. The velocity tells us the speed, like the magnitude of the speed, right? But it also tells us direction. This directionality component is so important. It's what distinguishes it from speed, yeah? Speed only has magnitude. Think of your car. If you're going 50 miles per hour, that doesn't tell you a direction, it's just telling you a speed. Velocity tells you a direction. As such, when we define our coordinate system, when we define where we start off for this sprinting and walking and which direction we go, that means that one direction will be positive and the other will be negative. So if this is my 0 point, I am going to say that walking to the right, to the right is going to be a positive value. But if I'm walking to the left, I'm going to say it's negative. And again, this positive and negative is how we tell the directionality. The positive or negative magnitude of the speed tells us its direction. So let's work through this example. All right, let's look at question A. The average sprinting velocity. Again, we are looking for average velocity. So average velocity is equal to the displacement over time. So when I think about this problem, I'm looking for displacement and time. We are told that the time, I'm going to use t here, is 6 seconds, 6.00 seconds. What about displacement? If we look at our handy dandy diagram, we see that I initially started out at the 0 position, and then I ran to the other side. So the final distance is 50 meters. Remember that displacement, or delta x, is x final minus x initial. So I'm going to plug this information into this equation. So I have average velocity equals, okay, delta x for displacement, so that's xf minus xi over time. So that's 50 meters minus 0 over 6.00 seconds. All right, so that's just 50 meters over 6.00 seconds. And I get that my answer is 8.33 meters per second on that sprint. If I can spell sprint. Let's look at part B now. Okay. So, there we go. Part B. We're asked to find the average walking velocity. So the average velocity during that second leg of the trip. I know that it took me 40 seconds to walk back. I know that my initial position was at the 50 meters. I know my final position was where I started. Notice here how in this part of the problem, the initial position is at the 50 meter mark and the final position is at that initial start mark, 0. So again, where you're looking at this coordinate system is important. The final versus the initial versus the final. All right. So again, we're just going to plug these values into our average velocity equation. So I have xf minus xi over time, 0 meters minus 50 meters over 40 seconds. Notice that this answer is going to be negative, and that's important. That tells us directionality. So when we plug this in, we find that the average velocity for walking, the walk back, was negative 1.25 meters per second. This was for the walk. And you might be saying, how can you have a negative speed? The plus and the minus tell you direction. The 1.25 is the magnitude. So you are traveling 1.25 meters per second in the opposite direction. So if you start at 0 and you end up with a positive velocity, that means you're moving in this direction, to the right. But if you were moving in the opposite direction, like during the walking portion, you're going to have a negative velocity. So again, positive and negative tell you direction. The magnitude, so like the actual number, is telling you the speed. Part C, the average velocity round trip. On first thought, you might think, average velocity. Okay, average velocity. Let's find the average of the sprinting and then the walking. But think back about what defines velocity. Velocity is displacement over time. Again, that displacement is important. It's not distance. What is your displacement if you go round trip? Your initial position and your final position, ooh, it's supposed to be an F, are the same. So if you start out at point 0, you end up at point 0. So for this, our delta x displacement is final minus initial. So that's just 0. We ended up where we started. Total displacement, 0. So it doesn't matter if the total time was 6 seconds plus 40 seconds, 46 seconds. When we plug this in to do the math, so average velocity equals 0 over 46 seconds, 0 meters. What does this go to? 0 in the numerator. This goes to 0. The average velocity round trip was 0. Here is our last practice problem for average velocity. It says, if the average velocity of your dog on its walk is 0, is the displacement positive, negative, or 0? Y'all, here equations are gonna be your friends for physics. If you're looking at this and trying to imagine this conceptually, like you walking your dog around the block, I recommend you also not only just draw out a picture, but also write out the equation. So let's say that I start with my dog here, and I go to this location, and then I walk back. So here's my little schematic to help orient myself. Also write out any relevant equations. I know that average velocity is equal to displacement over time. Next, I want to look at each of the variables and see how they function in the equation. Are they positive? Are they negative? Is it a big number or small number? Well, firstly, I know that time will always be a positive number. The total elapsed time for you to walk your dog is always a positive number. You don't come back and say, yes, it took me negative 5 seconds to walk my dog. So time is going to be positive. We are told that the average velocity is 0. So that means that we need to look at the relationship between average velocity and displacement. Time being a positive number cannot get us 0 average velocity. This is a positive number, and our end result is 0. So time doesn't really play a big role in thinking through this, okay? We know it's positive. What about displacement? Well, velocity tells us direction, right? So if we go to the right, to the left, down the street, up the street, but it also tells us something about the position, the displacement. What is our total displacement if I leave my house with my dog, walk around the block, and end up back at my house? Delta x is 0. Change in the displacement, the change in position is 0. Where I started was where I ended. Okay. So we just figured out displacement here. Ooh, we just answered our question. We know that displacement is 0. Boop. So if we look at this equation, what we're really working with here is average velocity equals 0 over some amount of time. Because we have that 0 in the numerator, average velocity goes to 0. So our average velocity for walking our dog was 0. I think average velocity is interesting to think about because it always kind of makes you sound like you just didn't move at all. But that's not necessarily the case. It's just that your change in position didn't move at all, which is pretty cool. This will be the last section for this set of lecture material, and we are going to talk about frame of reference. In a frame of reference, you are setting the perspective that you are looking at the world from. So the frame of reference is the coordinate system from which your perspective views the surroundings. For example, let's say that you are standing on the sidewalk. And you see cars go by. It's my beautiful car. Let's say it's going at 25 miles per hour. But you are stationary. You are at 0 miles per hour. Where you are standing stationary and constant, right? You're there. This is where you are viewing the world from, and you are not moving. You are viewing that car as it's going 25 miles per hour compared to your 0 miles per hour. How we set our frame of reference is very important because it can change how we analyze a situation in physics. So let's go through some more examples. So let's say you are on a moving train. It's my beautiful moving train. So you are inside the train, and so is your friend. Your friend has a baseball. I'm going to use green. It's a green baseball. And they throw the baseball inside the train, moving with the train. Let's say there's also a bystander who is stationary, like outside of the tracks. They're on the grass, just stationary. How fast that ball is thrown will look different for you on the train versus this person stationary outside the train. This is where frame of reference becomes important, because how we analyze the situation depends on where our frame of reference is. Do we want our frame of reference to be where we are inside the train? So we're treating the train as the constant. Do we want the frame of reference to be from this person, where the constant is the stationary ground? Let's see how it changes depending upon where we put that. Zoom in a little bit in my drawing. Okay. So here is the train again. And let's say that, okay, so you are here. Your friend is here. And they have that baseball, that green baseball. And they throw the baseball in this direction at 10 meters per second. Let's say that you are looking at the speed of the baseball in reference to the moving train. So imagine this in your head. Imagine you are inside this train and you see someone throw an object inside the train. It's going to look like, when we say reference to the moving train, that means we are treating that surrounding that train as a constant. Right? So if you're in your car or in a moving train and you throw something, it moves pretty normally, right? Like if you throw it at 10 meters per second, you're going to see it move like it's moving at 10 meters per second, because that is the perspective through which you're looking. It's all about comparisons, right? But let's say you're looking at it in reference to the stationary ground. So the ground is what is constant here. The train is what was constant previously. So inside the train, you see the ball going 10 meters per second. But if you're outside the train looking in, the ground is constant, the train is not constant. That train's moving past you, right? If you're standing there, that train is moving past you. So if someone throws an object inside the train and you're outside, you're going to see that ball move at 10 meters per second plus the train speed. See how these values change depending upon our frame of reference, where we're saying is constant, where we're saying is stationary, where we're setting our reference to. And it's okay if this is still a little tough and a little abstract. It's going to come with more practice of thinking about this stuff, okay? Let's look at this from the perspective of the Earth.